Hello everyone, my name is Taekyun Lee, and today I'll present our work, Efficient Weighted Sampling via Score-Based Generative Models. So just to start, the main goal is simple. We want to reuse a pre-trained diffusion model and efficiently steer its samples toward a task-specific weighted distribution, but without retraining. So we consider weighted sampling. So given a base distribution px and a task-specific weighted function wx, our target distribution is multiplying these two. So our target distribution qx is proportional to wx px. Here, wx can be represented. Wx can represent many objectives such as color, frequency, or human preference in like image or something else. So the challenge is that we do not want to train a new diffusion model for every single new weight function. And instead, we want to reuse the pre-trained score model for P and modify the sampling process to approximate samples from Q. So our method is called LAGS, which stands for Lightweight Approximation with Guidance Scheduling. So the target score can be approximated as gradient log Q, which is sum of gradient log P plus G tilde. And the first term comes from the pre-trained diffusion model, and the second term is guidance from the weight function. So a direct computation of this guidance can require Hessian vector products or expensive backpropagation through the score model. And LAGS avoids this using a Hessian-free first-order approximation. So in practice, it only needs one more score call, but not Hessian computation. So we also use a time-adaptive scheduler. And the idea is that we give weak guidance at early steps in reverse sampling and stronger guidance near the end when the denoise estimate is more reliable. So the key idea is that we are doing training free and Hessian free and resampling free with giving schedule difference. So we first test LAGS on a controlled 2D example. The base distribution is a Gaussian mixture, and the weight function defines a structured target distribution such as like heart shape and butterfly shape and those kind of things. And we can see that DPS misses much of a target structure. Freedom covers more area, but also generates samples outside the target. DAS is more accurate, but much slower due to resampling and also kind of biased. And our LAGS matches the target distribution well while being the fastest. So this shows that the lightweight approximation is still accurate enough for weighted sampling. Next, we apply LAGS to text-to-image generation. Here, the base model is stable diffusion, or SDXL, and the weight function is a PIC score, which is a human preference score. The x-axis is a relative runtime, and the y-axis is a evaluation score. So the best region is the upper left, high score and low runtime. And across both SD and SDXL, LAGS achieves the best PIC score and strong HPS, while also having the lowest runtime among guidance methods. And here are the qualitative SDXL examples. The top row shows the high PIC score samples, and the bottom row shows the low PIC score samples. The high score images better preserve the prompt details, such as the cat being inside the box near a window, or the object count for apples, like preserving this 3 information. So the PIC score improvement corresponds to visible improvements in the prompt alignment. And this slide shows another example with a prompt: a blue-furred tiger on a glacier. The base model often captures a tiger and glacier, but the blue fur is inconsistent, and DAS improves the blue attribute, but it requires more computation. And as you can see here, like most of the LAGS is more consistently capturing the blue fur while preserving the glacier scene without expensive particle resampling. Yeah, so to summarize, LAGS is a training-free, efficient, and scalable method. Thank you.